Okay, let me start integration by partial fractions. This is lecture 11, Calc 2. Partial fractions, you might have seen this in pre-calc, but I'm not sure. But anyway, that partial fractions relies on a fact from algebra, in fact, say abstract algebra, not the algebra that you know. It says that every polynomial can be factored into some linear terms and some irreducible quadratic terms. So if I have a polynomial like this, I can reduce it in this way, I can factor it in this way. So I have some linear term, this is a linear term, and since I have x to the power n and the coefficient is 1, every one of them has coefficient 1. And so I have some linear terms, and some of them might have exponent more than 1. Some of them might have exponent 1. And then some irreducible quadratic terms like this, and they also might have some exponent this 1 or something. The only thing that might be new to you is the term irreducible quadratic term. So let me erase this and define the irreducible quadratic term, because that's crucial here. So if I have, say, ax squared plus bx plus c, well, this can be factored anyway. But the two factors might be something like this. So this gives me two solutions, two roots, say x1 and x2, right? So this will be x minus x1 times x minus x2. Now the x1 and x2 can be real or complex. So if x1, x2 are both real, they are either both real or both complex. Both real, we say that it is reducible. If x1 and x2 are complex, we say that it is irreducible. Now, why we say irreducible? Because you might say, gee, we did that, we factored this. True, but since we are dealing with the real numbers, so we just call this irreducible. Yeah, if we are doing like complex analysis, then yeah, that is okay. We can have something like that. But we are dealing with just the real numbers, and so we call this one irreducible. But when do we have complex roots? So when do we have complex roots? Let's look at the quadratic formula. Quadratic formula is this, minus b plus minus b squared minus 4ac divided by 2a, right? It becomes complex if this b squared minus 4ac is negative. So b squared minus 4ac bigger than or equal to 0, real roots, let's say, real roots, real roots, and if this is negative, complex. So when you are given a quadratic function like that, you can find b squared minus 4ac. If that is less than 0, then it has complex roots. So it cannot be factored with real, say, linear components. So let me give you some examples. examples of this thing. So x squared plus 2x minus 3.5 something. Whenever this constant term is negative, it has real roots. Why? Just look. B squared minus 4ac, you see this is minus. So if this is positive, this is negative, then this will be positive. So look, this is 2 squared minus 4 times 1, the 1 is here, times minus 25, right? So this minus and minus will give me 4 plus 100. So this minus and minus gives me a plus here. And this one is also positive because it is something squared, so it is bigger than 0. So if you see this, then it is telling you that this is reducible. So if this is negative, if C is negative, it is reducible. Okay, so by C I mean this, ax squared plus bx plus c, and I'm assuming that a is bigger than 0. So let's assume that a is bigger than 0. Always, when you are given a quadratic, if this has negative coefficient, just multiply it by -1, or let's say factor a -1, so the inside is positive. Anyway, so another example too. Now, what if this is positive? Well, sometimes it is, sometimes it isn't. Now, sometimes you can factor this without writing the quadratic formula. If you look at this thing, before doing anything, just look and say, okay, two numbers that when you multiply, you get 6. That is 2 and 3. 2 plus 3 is 5. Okay, so there is nothing to do here. We just factor this thing as this. This is positive, but we can factor it in with real factors. Let's look at the b squared minus 4ac. The b squared minus 4ac will be 5 squared minus 4 times 1 times 6. So that is 25 minus 24. Okay, so that can be factored, and in fact I factored this thing. Number 3, again, let's look at another one which has a positive here and see what we can do here. So number 3 is say x squared plus 2x plus 2. Can you factor this thing? 2 is 2 times 1, right? That's all we have. 2 plus 1 is 3, not 2. So let's do something else. So the b squared minus 4ac will be 2 squared minus 4 times 1 times 2. So that is 4 minus 8 less than 0. So this is irreducible. Well, this was reducible, obviously. Irreducible. Okay. So if this constant c is positive, assuming that a is positive, if this constant c is positive, then you have to check. If constant c is negative, then that is irreducible, and that is reducible, and you can use either like this. You can factor it if you know if it can be factored easily. Otherwise, no. Well, you have to write down the quadratic formula. So let me factor 1 for you. 3, 4. So if I have, let's say x squared plus say 3x minus 5. So roots are x is minus 3 plus minus b squared is 9 plus 4 times this 20, right? Divided by 2. So x is minus 3 plus minus 29 divided by 2. So it is minus 3 over 2 plus and minus square root of 29 over 2. But we can write it like this or we can write it like that, no difference. So this factors this way, x minus x1, what is x1? x1 is this, plus times x minus x2, which is minus 3 halves, minus. Okay. And if you are given anything like this, then my suggestion is not write it like this. Don't apply the negative. Write it like this, so this is before your eyes, and this is in fact one of the roots, x1, and this is your x2. Okay. So let me double check and see b squared minus 4ac for, that's correct, I guess, yeah. Anyway, so that is how you factor by finding the roots, and so that's x minus x1, x minus x2. Now if the coefficient of this is not 1, still we can do that, but if that is not 1, my suggestion is just divided by that coefficient. Then, so if you are given, let me do another one, maybe it helps. So let's say number 5, let's say we have 2 here, right? Let's say we have 2. So, well, let me erase this. So what we do here, we first factor 2. So this is x squared plus 3 over 2x minus 5 over 2. So the inside this one as roots without the 2 is minus 3 over 2 plus minus 9 over 4 plus 20 over 4 divided by 2. So that is minus 3 over 2 plus minus, this is 29 over 4, so 1/2 square root of 29 over 2. So just divide 1 by 1, 3 over 4 plus minus 1 over 4 square root of 29. Okay, so this factors as, let me write it here, 2 times x minus, say minus 3 over 4 plus 1/4, 1/2, sorry. Oh, that's correct, 1/4. 1/4, 29 times x minus the other one. So let me double check, 3 over 2 minus 5 over 2, so I have 9 over 4, and oh, that's not 4, right? 4 times this, that's 20 over 2. Is it, let's see, that's 9 over 4 is correct. 20 over 2, that's not 4. 20 over 2. So I will get something else here. That's 3 over 2 is okay, then that is 18 and 38. 38, right? But this is 4, then I have, no, it's 9 plus 49, no, that's okay. 7 over 2. It's interesting that is 7 over 2. So, well, I guess we had nice, that's much nicer. So, double checking. So that is the 49 over 4, and that's 7 over 2. So the answers are minus 3 halves plus 7 halves over 2. That is 7 minus 3 is 4 over 4, that is 1. And the other one is minus 3 halves minus 7 over 2 over 2. That is 10 over 2, 5 minus 5 over 2. But let's hope it's correct. So anyway, so that is 2 times x minus 1 times x minus 5 over 2. So it is 2 times x minus 1, x plus 5 halves. Yeah, I guess that's quite good. But just accident that has a nice say. Well, anyway, so that's how you do that. You have to pull this coefficient out, so you factor this, then you do everything to the inside, and this 2 stays outside. And in the end, don't forget to write that 2. Okay. So that was a nice example. Now, using this, we have another fact that this is in fact partial fraction. If I have, say, some say gx, for example, a polynomial. So let's say gx is a polynomial. Now this polynomial can be 1. 1 is a constant polynomial. Many times it's just a 1 here. But, and the denominator is a polynomial like this, x2 plus a, what was that, a1, no, what x2, xn, n minus 1 plus a2, xn minus 2 plus up to a0. And we know that we can factorize this thing, the denominator, as something like this. Remember, we factorize x minus x2. This is n1, this is n2, and and I have x squared plus, say, what was that, mx, plus, say, r power s1, and so on. So, now this is equivalent. This is equivalent, not equal, equivalent to this. For every factor that has, for every linear factor, I have something like this. So I have like a1 over x minus x1, a2, x minus x1 squared, up to a n1, this exponent, x minus x1 to power n1. And the same happens to this one, b x minus x2, b1 say, plus b2, x minus x2, what was that, n2, no, 2, up to, say, b n2, x minus x2 to power n2, say. And this continues until we get this. So this one also, something similar happens, except we have something like this. So we have c1x plus d1 x squared plus mx plus r power 1, then c2x plus b2, this one power 2, and this continues up to power s1. So for every factor like this, we have, if that's the exponent is n1, we have n1 components. And also, if this is s1, we have s1 components like this. And those components have this thing in the denominator, starting with exponent 1, ending with exponent n1, and the other one too. Now, when I say it is equivalent, I mean this side and this side are the same. That's like it's not the, let me explain. It's like an identity. So if a plus b, for example, I say a plus b squared is a squared plus 2ab plus b squared. And I write this, which means the two sides are exactly the same. Or in other words, for any a and b, they are the same. For any a and b, they are the same. But if I write x plus 3 or 5, this is true for only one x, and that is 2. If I write a quadratic equation, x squared plus 5x plus 6 equals 0, then it is true for 2 x's, and so on. So these are equations, these are equivalents, or let's say these are identities, which means they're identical, the two sides are identical. Now I'm saying that this thing here, or this thing, is identical to this. I'm not solving an equation, I'm saying it is exactly this. Okay, let me give you examples of what I mean. Well, I don't think anybody will has to, find the partial fraction of such a complicated, rational function. This is a rational function. Rational function has polynomial here and polynomial here. That's why I assume that gx is also a polynomial. So let me erase all these things here. Examples will clarify. So let's start with the simplest, x minus 5, x plus 3. That is, what was the 1 here? Let's write 2x plus 2 something. Instead of something. So that is a over x minus 5 plus b over x plus 3. And be careful, this should have, the degree of this should be less than this. I forgot to write it in that equation. The degree of gx should be less than the degree of the denominator. Okay, so degree of this one should be less than this one, otherwise you have to divide and get rid of that extra thing. But usually you don't get that, so usually you have something like this. So that's the simplest case. 2, let's say I have x squared plus 3x minus 5, say something, and denominator is x minus 1 times x plus say 5 times x squared plus 2x plus 2. And remember, this was one of the examples, and it is irreducible. So this is equivalent to saying a. And remember, this has degree 2, this has degree 4. 1, 2, that's 4. So that is x minus 1. Well, let's write 2 here, okay? So This is just 1, so then I have b over x minus 5 plus 5, then I have c over x plus 5 squared, then this one plus dx plus say f x squared plus 2x plus 2. Okay? This might be the hardest you can get. I mean, polynomials like this irreducible to powers more than 1, it doesn't happen too often. But this one would happen. So this, in fact, this is not a simple problem to solve. No, it's simple, but it takes time to find these coefficients. So this one equivalent to this one means what? Means you have to find A, B, C, D, and F such that this equivalence happens. So your job, or less partial fraction, is this in fact. The problem related to partial fraction is writing this in this form, then finding these unknowns. So I have 5 unknowns here, and these are just numbers, and I have to find them. But how do we find them? It's very simple. You just put these together, and then the denominators are the same, so the numerators should be equivalent. Now I will do an example. So let's do this one. So examples. Let's say example number 3. So this side, let's put this together. It is a times this, x plus 3 plus b times x minus 5, and denominator is x minus 5 times x plus 3. Now there's a trick here, which I will use the trick. And the trick is, well, this numerator, the denominators are the same. So this implies that 2x plus 31 should be the same as this. A times x plus 3 plus b times x minus 1. Now one way to solve this is just simplify this. So I will expand this and regroup. So I have a plus b times x plus 3a minus 5b. Okay? And then say, okay, since these two should be exactly the same, then the coefficient of x here should be equal to coefficient of x here. And the constant term should be equal to the constant term. So this gives me 2 equations in 2 unknowns. This should be exactly 2, and 3a minus 5b should be exactly 31. And solving this system, you will get a and b. So that's one way to do it, and some students prefer this. I've seen whatever I say, they just do this. And unfortunately, many students who try this thing, for whatever reason, they make mistakes. Well, at least those who are taking the exam in a fixed period of time. But since your exams are like kind of online and you have more time to do it, then maybe you won't make those mistakes. But please, if you use this method, please be careful when you solve these simple systems of equations. Another thing is like this, and don't ask me why this happens. Let me erase this and say, okay, another way is to say, okay, these two are the same, which means they should be true for every x. One might say, okay, they're not true for x equals 5 and x equals negative 3, because that makes the denominators in 0, so I get infinite. But there's a trick anyway. So I do this. First of all, I want to make this 0 and find b, then make this 0 and find a. It's that easy. How can I make this 0? So let x be negative 3. Then this side will give me 2 times negative 3 plus 31 equals a times 0 plus b times -3, -5, right? Now this side will be -6 plus 31, and that is 25, right? So I have 25 here, and on this side I have -8b. So this gives me b is -8/25. Let me double check. So x -3 will give me -8 over there, and this on this side. -6 plus 31, that's 25. So I found b. Now let x be 5, so make this one 0. So let x be 5, then I have 2 times 5 plus 31 equals a times 5 plus 3 plus b times 0. So this side I have 10, that is 41, equals 8a. So a is 41 over 8. Let me double check. So in the end, these two are in fact what was a? And write it like this: 41 over 8. X minus 5, right there. If it is a fraction, write it in the numerator as a fraction. That's just an important piece of advice. Then this is minus, but that's okay, right? Plus -8/25 divided by x plus 3. Don't write it as 8/25 times x plus 3, okay? Write it like this. And if this is negative, don't put negative here. Negative here. Okay, so now if I am supposed to integrate this thing, so let's integrate. So if the next step is integrating this, say, this rational function, 2x plus 31 over x minus 5, x plus 3 dx, and that is, I say, okay, I know it is this thing, so I have two integrals, 41 over 8 over x minus 5 dx plus integral minus 8 over 25 x plus 3 dx. And you can see why I said write these two as is on top, even with the negative sign, and put positive here, plus here. So the first one is ln, right? And that's just a constant. Ln of absolute value x minus 5. The second one is also ln, and that is minus 8 over the, what was that? 8, that isn't that 25 over 8? You see how that was 25 over 8. That one, why to make this thing? Minus 25. If I wrote that 8 over 25, that was wrong. So that is 25 over 8. Minus 25 over 8 ln of x plus 3 plus a constant. And that's it. That is, it's finished. Some people, if these coefficients are nice, they would just put these two ln's together, but these coefficients are something. So in some special cases, it's good to bring this coefficient. But by this, I mean writing this as ln of absolute x minus 5 to this power. Remember, the power here comes here. And this one, I can just put this power, the negative outside, and write it as ln x plus 3 to this power. 25 over 8 plus the constant. That's what I mean. Then you can put these two together. This is ln of this divided by this. But that's okay. Just leave it like this. Or this. In fact, this is good. Unless, as I said, unless these are nice coefficients like 1/2, then you will get a nice expression here. Okay, so that is how you integrate a rational function like that. So let's integrate another one which has, like this one is, for example, square. Well, I can do that. Let's just use the same. Let's put square here. Okay. So that's example number, in fact, 4. Let's do the same thing. So I have a b, and let's change that 31 to a nice number, smaller and nicer number. So let's write a 6. So what else should I add? C over x plus 3 squared. Okay? So let's put that together, and remember, when you write this, the denominator is exactly this. The denominator should be exactly this. So be careful. Sometimes students just, when they put them together, they multiply this thing, and the denominator will be x plus 3 to the power 3. No, it's not. What they do. Just one of them. That's what you shouldn't do, in fact. You shouldn't write it like that. So it is in fact this. Now, so I have this divided by this will give me x plus 3 squared. This divided by this will give me b. This remains at one factor here, x minus 5, x plus 3. Then c, this thing divided by this will give me simply x minus 5. Okay, so and this is equivalent, and so 2x plus 6 is equivalent to this, a times x plus 3 squared plus b times x minus 5 times x plus 3 plus c x minus 5. Let's do the same thing. X equals, let's put x equals 5, so I find a first. X equals 5 will give me 10, that is 2 times 5 plus 6 equals a times 5 plus 3 squared, and plus this is 0, plus this is 0, right? So 5 plus 3 is 8, squared is 64. This side I have 10, 16, so 16 is 64a, and that gives me a is 16 over 64, and that is in fact 1 over 4. X is negative 3, so let's find another one. 2 times negative 3 plus 6, oh gee, that's 0. No, I don't want 0 here. So let's change something. So I don't want 0, because anything is always 0. So let me change this to, say, 8. So this will be 8. So I have 18 over here, not 16. And that is 18 over 64 divided by 2. I will get 9 over 32. Okay. 2 times 3 plus 8 is, when x is negative 3, this is 0, this one remains. So that is c times minus 8. So this is 6, 2, so that gives me 2 equals minus 8c, and that gives me C is minus 1/4. What would happen? Oh, 2x plus 6. 2x plus 6 was a factor of this. Oh, I see what happened. Why that C was, yeah, that was in fact incorrect. You see, if I have written that would be 2x plus 3, and there's an x plus 3 here. Before doing anything, you have to simplify. So that would be just 2 divided by this times this. That x plus 3 would simplify to just one exponent. That's why the C would be 0. Okay, so I should be careful next time when I write something on the fly. Now I have found A and C, so how can I find B, the middle one? Well, there's no other root left here. But I can use any x equal anything. So let's use x equal to 0. So 0 will give me, on this side will give me 8. On this side I know A is 9 over 32. And that is 0 plus 3 is 3 squared times 9. Then plus B, I know B is unknown. B times 0 minus 5 is minus 5 times 3. And C is minus 1/4 times negative 5. Okay. So, let me write these on top here. So I found A is 9 over 32, so let's put 9 over 32 here. And I found C is minus 1/4. So let me erase everything and solve this this one here. So the only thing that remains is this one. Let's hope things are right. Check my calculations. So I have 8 on this side, and this is 81 over 32, and this one is minus 15b, and that is plus 5 over 4. Wow. Okay. So 15b is 81 over 32 plus 5 over 4 minus 8. 32, that's 81 plus 8, 40, and 32 times 8, oof, okay, so minus 25, 156, right, that is 64 times 4, yeah, and so that is 256 minus 256 minus what? Minus 121, is it? 121, right. And I have 5 here, and I have 3 here, 135. So that is 135 over 32, and B is in fact, the 32 stays here. And 135 divided by 15, so by 5, this will give me 3. So I guess that's divisible by 15, right? So let's divide by 5 first. That is a 2, 7. Then divide by 3. That is a 9. Yeah. So 9 over 32. Oh, let's hope these are okay. We can use Wolfram Alpha to find this thing. 9 over 30. Now I have a reason to do this to the end. Okay, so we have found coefficients. You can check this with Wolfram Alpha to see if my coefficients I found are correct. And so what is the integral of this guy? that's this one. They're both 9/32. Oh, should I get rid of the thing? So, okay. But the point is not finding them because you can just use any computer algebra system like mathematical or online or from alpha and find them. The thing is that the integral. So the first one will be 9/32 ln of x minus 5. The second one is again something like this, ln of x plus 3. What is the third one? Minus 1/4 what? And be careful, I have seen students writing that as ln. That is not ln, please. ln is when the denominator is a linear function. A linear function. Please, please, please. Don't just write ln whenever you see something in the denominator. Okay, so that is in fact like the integral of 1/x squared, right? So that is 1/x plus 3 squared dx. So it is something like this, integral of x plus 3 to power negative 2 dx. You can write u here, so this is like u minus 2 du. If you put u here, then dx is du, and that is 1/-2 plus 1, u minus 2 plus 1. So it is minus u negative 1. That's minus u negative 1. So that is, there's no absolute value here, x plus 3 to power negative 1 plus c. Okay, so ln only comes into the picture when the denominator is linear. So if the denominator is degree 2, degree 3, or whatever, then don't write ln. Please, please, please. That is not always ln. Okay. So I hope I didn't make too many mistakes. Well, at least I know that this is correct, except the coefficients might be wrong. So check the coefficients using like Wolfram alpha. And so let me write down those. So I still have to do another example with coefficients. I mean the denominator having an irreducible factor. So if I have f prime x over fx dx, this is ln of absolute fx plus c. But if I have something else here, gx over fx, or a constant, because they're not a constant, say 1, right? 1 is not ln of fx unless fx is a linear function. Okay, unless fx is a linear function, like what? 1 over, say, ax plus b, this is the most general form, and that is in fact 1 over a ln of ax plus b plus c. So you can just, now if a is negative, negative 1 for example, an example of this is something like this. If I have 1 over 1 minus x dx, that is minus ln of 1 minus x plus c. You see, in this case, this negative in fact is this a. So I have 1 over minus 1. 1 over minus 1 is minus. So be careful. If you have negative x in the denominator, then that is minus ln of the absolute value of that. Okay, so let me stop, and I will continue this with, I just need to give you another example, and then I'm done with this integration by partial fractions, and basically almost we are done. So, okay, so see you next time.